Hi there. In the first video, we made the box plot that you can see on the screen. Now, when you go back and look at the original data though, this minimum of -8 is quite a ways away from the other values in the lower 25%. The next closest value is a -2. So that makes me think that this -8 may be an extreme value. Another term for that is called an outlier. So there are mathematical criteria that we can use to determine whether a value is an outlier or not. So you can have an outlier that's really far to the left, so a really low value like -8. I suppose on the other side, we should check, we could have an outlier, this 6 for instance. It's not too far from the 4, but 6 is relatively far from the 0. So maybe this is an outlier to the right. So we have to have a way to determine how extreme is extreme enough for us to say that we have an outlier. So here are the actual criteria. All right. So if you have an outlier to the left, you have to have a value that's pretty far below Q1. So what we do is we start at Q1 and we subtract an amount off of Q1 to create what I like to call a lower cutoff. So this lower cutoff value, to calculate it, you use Q1, but then you take away 1.5 times the interquartile range, 1.5 times the IQR. So essentially what we're doing is we're taking the interquartile range, that's 3 units wide, we are increasing it by 50%, that's what multiplying by the 1.5 does. So we're taking this interquartile range, essentially we're making that distance 50% wider, and then we're taking that distance and tacking it on at the bottom of Q1 and creating a lower value. So let's actually calculate it. The value of Q1 is at -1. Then I'm going to subtract off 1.5 times the interquartile range. We calculated the interquartile range in the last video as 3. You could actually count the units here. Each of the boxes represents 1 unit. So it's 1, 2, 3 units long. So -1 minus 1.5 times 3. 1.5 times 3 is 4.5. So if I subtract that from -1, that gives me -5.5. So what this tells me, any value, here's where -5.5 would be. Any value below -5.5 is considered an outlier. And you can see then that our -8 is less than that cutoff of -5.5. So that means the -8 is an outlier. That's why I did the box and whisker plot in pencil, because an outlier is actually represented in a different way graphically. So I'm going to erase the dot that I put at -8, and instead I'm going to put a box there. That box represents that we have an outlier. Now, then the next question is, where does this whisker now stop? Well, the -8 is an outlier. The next lowest value is a -2. So in fact, this whisker should stop way, way, way back here at -2. I'm going to erase all of this. Now you can see why it was important. It was important to actually label the outlier, because having the whisker that was this long was suggesting that there are data values in this span right here, and there weren't. The -8 was very far to the left. The next lowest value was -2. Having that really long whisker there was misleading. So this is a better representation of the actual spread of the data. I get a better idea of where the values are positioned within the range of -8 to 6. So we can also have outliers to the right. So it's very similar. I call this the upper cutoff. So similarly, instead of starting with Q1, we're going to start at Q3, and we're going to add 1.5 interquartile ranges above Q3, and that's going to make our upper cutoff. So Q3 plus 1.5 times the IQR. So Q3 is at 2 plus 1.5 times my interquartile range of 3. So 1.5 times 3, that's 4.5 again. So if I add that to 2, that gives me 6.5. So notice that would be right here at 6.5. The last value of data, the farthest value of data to the right is at 6. So the cutoff for an outlier to the right is at 6.5. I don't have any values in this data set that exceed 6.5. So there are no outliers to the right. So it's important to check for outliers. So again, those criteria, Q1 minus 1.5 IQRs, that's your lower cutoff. Q3 plus 1.5 IQRs, that's your upper cutoff. And understand then, now that we have the outlier labeled and we have a whisker of the correct length on the left, now you can see how this graph is very useful for understanding the shape. This is not a particularly symmetric distribution. In particular, I would say the shape of this distribution is skewed to the right. The shape is skewed right. And now I can see the skewness. So notice right here, this whisker is quite small. So again, this 25% of the data only spans the distance from -1 to 0. Then the next 25% of the data is stretched out. It spans from 0 to 2. The last 25% of the data then is stretched out even farther. It spans from 2 to 6. So notice, as you look at the graph from the left to the right, it is stretched out to the right. That is the direction of the skewness. So notice the data, 50% of the data is clustered right here. And then the upper 50% of the data starts at the median and stretches all the way out to the maximum of 6. So there's a clump of data, if you will, on the left, and then it stretches out to the right. So this plot does show you, now it's important to have the outlier marked so you don't have that crazy long whisker over here on the left, but this is a good example where the box and whisker plot not only can show you where the data are positioned, but because of that, it can show you the shape of the distribution. This would be an example of skewed right. Click on the next video then, and I'll show you how you can create this exact same graph on your calculator, and that's what I would encourage you to do on your homework assignment.